It is my pleasure to announce today the talk by Dr. Jörn Wichmann from Monash University. Jörn obtained very recently in 2022 his PhD degree at the Bielefeld University and then got a position at Monash. Jörn works on numerical methods for stochastic PDEs and also for related problems of regularity of solutions to some strongly nonlinear stochastic PDEs, such as stochastic P-Laplace equation and also non-Newtonian fluids. Please start.
Okay, thank you very much. I hope everyone can hear me. So in today's talk, I'd like to speak about regularity results for generalized fluids. And this is joint work with my former supervisors, Martina Hoffmann-Hover and Lars Diening, as well as ongoing work with Jérôme Dronieux and Nang Li from Monash University, where I'm right now sitting. Yeah, let's just start. I want to briefly explain why should we care about nonlinear systems of equations, and in particular, why should we care about nonlinear systems of equations under stochastic perturbations? So in the image on the top, you see a evolution of a fluid, which at first, so you have like a flow from the left to the right in a pipe, and at first you have an inflow of the fluid, and you can nicely see a laminar evolution of the fluid particles, meaning that they follow the streamlines nicely. And after some amount of time, you see that tiny vortices might appear and get bigger and bigger and bigger. And after like a critical amount of time, one cannot see anything anymore, and one just has turbulent evolution of particles. So this is like a prototypical evolution of a flow. And in particular, to capture the evolution of fluids mathematically, it is quite difficult to model both the laminar flow on the left, so laminar flow, and the turbulent flow on the right. And especially as we are interested like at the forecast of particles, so if we know the evolution of a particle at time t and x at this position, we need to know where is the position at later times. So this is used in weather forecasting, in many situations, and therefore we need to come up with like stable approximations that are really, really robust, and in particular do not suffer from this mathematical turbulence problems. On the other hand, it is not only so it depends on what fluid we put into the pipe. So if we have this fluid, this pipe, and put water in it, water behaves substantially different compared to like gases, or like we could also put concrete into the pipe. We just collect all those different types of fluids, and we could and call them fluid, but they have substantially different behavior when it comes to its reaction to different scenarios. So if you look to the left, this is a diagram where we have like the action of the shear stress that a fluid undergoes with respect to the shear rate. And here the var epsilon u is the symmetric velocity gradient. And in the classical case where we have Newtonian fluids, we know that the shear stress is just a linear function of the shear rate. So meaning we follow this straight line. But there are different kinds of fluids, meaning that the shear rate is not a linear function of the shear stress is not a linear function of the shear rate. And here's just a collection of different fluids following different laws. So there are the Bingham fluids, shear thinning fluids, shear thickening fluids, and many more. And not only are we interested from a mathematical perspective on these different kinds of models, but they have real-world applications. So if we look here to the right, we can just measure from different fluids its respective relations, and therefore they are naturally there in the nature. But also if we want to engineer specific fluids for different purposes. So for example, if you want to paint the wall, we want that the paint is not dripping as soon as we push it, like apply it to the brush. But if we want to then apply the paint to the wall, it should stick to the wall, meaning that at first it should not drip, but as soon as we apply a slight pressure, it shall become more viscous. So it's shear thinning. On the other hand, shear thickening. So we want to, like, if we want to create a body armor which is like flexible, meaning that we can move freely, it shall be like under small stresses, it should be really, really viscous. But as soon as like a shot is shot, it should get like hard, because otherwise the pattern would just go through the armor, and it's dangerous. So you shall better have the flexibility, but on the other hand, you want the protection. So we care not only from a mathematical point of view, but also from an engineering point of view to understand fluids. Now I just have showed you some images and have not said anything about what are the mathematical description of the fluid. Let us first try to understand why shall we care about stochasticity. So on the microscopic scale of a fluid particle, so we just sit ourselves on a particle. For simplicity, now we assume that the particle follows the evolution of the heat equation, undergoing with some force term F. On the microscopic scale, each particle lives on its own. And there are many reasons to say that as soon as we are on the macroscopic scale, that we add a stochastic perturbation that basically pushes the particle in a random direction. So this psi is white noise and just tells you, okay, go in any direction with the same probability, but on average you do nothing. So this is just a ground fluctuation of particles in a sense. If we leave this microscopic scale, so we do no longer consider each individual particle, meaning that you do not have neighbors, but we just enlarge our scale to a larger bracket, here indicated with the gray area. So we no longer see each individual particle evolution, but see more like an ensemble of particles. Then one observes like a microscopic evolution of the particles. So because this psi on each particle is a random push in the direction, but on average you don't push anything. So if we average this equation, so we apply a bracket operator, the average of psi is just going to be 0. So the macroscopic evolution of the equation might look like this. And because fluids lie kind of like in between the evolution of microscopic and macroscopic, depending on what we want to observe of the fluid, Mikulevicius and Rosowski in our form proposed to supplement the classical Navier-Stokes equations. So the left-hand side of this here is just classical Navier-Stokes, but we should enforce the equation by this kind of transport noise. And they argued that in the classical derivation of the Navier-Stokes equations, you assume initially to have a sufficiently regular velocity field U, and then you can say, okay, based on the conservation of momentum and the conservation of mass, you shall arrive with this equation and the divergence free, so the incompressibility condition. But if you not start from a smoothness assumption of the underlying velocity field, but rather you have a decomposition into a smooth contribution and a contribution that is rough on the scale of dW, you shall come up with exactly this kind of stochastic source term on the right, meaning that you have a transport noise in Stratonovich formulation, and because you want to preserve the incompressibility condition, you also need to prescribe that the transported random velocity field here has the 0 divergence. So we on the next want, so this is the classical evolution, or more or less classical evolution of Newtonian fluid flow. Non-Newtonian fluid flow, we have seen that the shear stress is not in linear relation to the shear rate, meaning that exactly this diffusion operator, where the Laplace is sitting, needs to be replaced by a more general operator, divergence of the viscous stress S. And because we want to do like mathematical theory, we do not really care about the specific structure of the right-hand side here, but we just call it G of U. We will consider G of U in the E2 formulation rather than the Stratonovich formulation. So the Stratonovich formulation is usually preferred from physicists because it allows for the classical chain rule to apply and have different other advantages. But mathematically, usually the E2 formulation is like favorable because there you have like nice martingale properties you can exploit. Yeah. So if you want to think about this general G of U, think about the gradient structure. However, in most of the examples I will show you later, we cannot treat gradient type of noise, but are more or less restricted to noise that is almost linear in U. But we should keep in mind that later on, we want to try to generalize certain results to gradient type of noise. Okay, so what is now classical non-Newtonian fluid flow? So this is the generalized Navier-Stokes equations where we are seeing that we replace the classical Laplacian. So the Laplacian of U needs to be replaced by the viscous stress here, which is a function of the shear rate, which is the symmetric velocity gradient. And we replaced our right-hand side by a general G of U, which depends on the Brownian, on white noise, basically here. So this top equation is very, very difficult because you not only have the nonlinearity coming from the convection, but you also have the nonlinearity, even though this has a sign. So this is it is a monotone operator, which gives you, depending on the value of this P. So we see here the P. If P is large, you get more and more like regularization. If P is small, as we have seen last week, P equal to 1 is really, really difficult. You lose some regularity. So this is a troublemaker because it is a nonlinear operator. This is a troublemaker because you need to leave the nonlinear, the linear theory. Yeah, and this is a troublemaker because you cannot just apply deterministic theory in order to come up with regularities results. So maybe a first way to simplify the equation to understand how we should generalize theory from classical, so either deterministic parabolic theory or even deterministic evolutionary theory, so deterministic theory for evolution equations, we maybe first should simplify the system we consider and then try to like generalize. So from here to here, if we just assume that this convective term is negligible, so we just cross it out and say, okay, let's say this is a reasonable approximation. Applying the Helmholtz-Larrey projection to the first equation, we can nicely factorize the equation for the velocity field, so the velocity field U and the pressure pi. And why do we do this? We do this because this velocity equation is like a nice monotone equation where we have classical theory. And on the first, so understanding the velocity equation here basically boils down to understanding the P Laplace equation here. So if we don't care about the projection and say, okay, this is the first order approximation, also, so here on the bottom, we should first understand how is regularity preserved for the P Laplace system. And then maybe we can say something about, okay, what is now a consequence, what is preserved for the P Laplace, for the P Stokes equation. And then the next step would be, okay, what can be generalized from the P Stokes equation to the P Navier-Stokes, the generalized P Navier-Stokes equation. And in the end, if we want to do forecasting, we need to use the understanding what we gain from the regularity in order to build robust algorithms that give us in the end an accurate prediction of the future. So meaning if you want to either do the large scale for weather forecasting, so we need to come up with robust schemes, but also like tiny scale. If you want to understand how blood evolves in like a vessel, we shall also come up with a robust algorithm. And blood is in general a non-Newtonian fluid that follows like some law of this type, where this P, I think, shall be bigger than 2. Yeah, and why is it difficult? So as soon as we leave the linear regime, things become difficult, so that you have no longer like a nice relation between data assumptions and solution regularities. And the second difficulty is that we have rough data nevertheless. So assuming that the data is smooth is not reasonable because our right-hand side depends on the Wiener process, meaning that usually you have a threshold on the level of regularity of a Wiener process. And that's why the solution itself, U, will only have limited amounts of regularity. So it's like the question, can we find algorithms that work with this limited but reasonable amount of regularity and still get like the right convergence results? So why shall we care about regularity? If we want to find the accurate approximation of future states, that's in general a guiding principle. If you have regularity, meaning that the function cannot change too fast, then you can find finite amounts of building blocks that approximate the function accurately. So a classical example is if you measure regularity on the Sobolev scale. So for example, you take a function that has k derivatives that are in L2, then you can find a polynomial of order k minus 1 that is exactly close to the quantity you want to approximate U up to an error of order k. So if the right-hand side is bounded, meaning that this guy is a regularity assumption, essentially, regularity assumption, then you can approximate this function U by polynomials. And how close you are is exactly measured in this mesh condition, meaning that if you take sufficiently many, this one will decay rapidly. And this is like the backbone of a priori error analysis. And how is this applied in the context of PDEs or SPDEs? On the example of the classical Laplace equation, solve this Laplace equation, take a discrete subset, so a conforming discretization, solve this discrete problem, and then you can check that the gradient error you do is nothing but the best approximation in the space. So first you just take an arbitrary conformal subset. The best approximation you get is exactly the solution to this discretized equation. And only afterwards, you take like regularity in order to bound exactly this. So meaning that now if you have sufficient richness in the approximation class, so if polynomials of degree pk minus 1 are included, then you just take like this polynomial here. If you apply this here, then you get this bound. And you get exactly this a priori result. And now regularity kicks in because regularity theory tells you that the solution map that maps exactly our data f to the solution of u is kind of bounded. So meaning that you can replace the k derivative of the solution u, where you don't have access to because you don't know the solution, otherwise it's pointless to approximate it. But what you know is the data. So now, if you know the regularity of the data, you know how to need to choose your mesh condition in order to make the approximation you want to have below a certain threshold, meaning that this shall be below a tolerance. So it is key to understand exactly this condition, meaning regularity gives you approximability. Okay. So the next step is to kind of understand what are natural quantities to consider in the nonlinear framework if you want to express regularity. First of all, I want to say something on these two kinds of problems, namely first, nonlinear. Nonlinear means that in general, smooth data does not give you smooth solutions. Maybe to point out, this one is exactly the result that refers to the first line here, because in the result of Vianic and Manfredi, they considered the plane and considered p-harmonic functions in the plane, and they have a precise formula what regularity does a p-harmonic function in the plane has. And in particular, since the right-hand side is 0, it is smooth, you have a threshold on what regularity there is. So there's U can be in WKP, and for K and P, you have a formula, KP formula. In particular, you cannot just choose arbitrary Ks and Ps. It is like a classical, so for just to say some positive results, it traces back to the 70s, Ural-Sever, Uhlenbeck, and Di Benedetto. They considered like what regularity can we get for systems, but on the level of U and gradient of U. So they asked, is the function continuous? Is the function Hölder continuous? Is the gradient continuous? Is the gradient Hölder continuous? But it turns out that if you want to do numerics for like P-Laplace type of equations, the natural quantities to consider is like the square root operator of the operator S. And this was done the first time by Barrett and Leo in '93. And they showed that, for example, this V operator, and by the way, V is related so you have the operator S of A minus S of B tested against A minus B is exactly V of A minus V of B squared. And here you have some equivalence constant. But the key point is that this kind of like transfers the nonlinear operator S into a Hilbert setting. So because you now measure it on L2, but you need to measure it in nonlinear quantities, namely VP. And this has been extended to parabolic systems by Diening, Eckmeyer, and Ruzicka. And only recently, people became interested in, okay, you can do like a regularity theory for the square root operator V. What can we say about the other operator S? And this has been done by Chunky and Mazia or Balchi and all. And they showed that, okay, if the right-hand side, so this is for the stationary problem, if the right-hand side is in L2, they showed that the gradient of S itself is in L2. So meaning that you have a strong, so not only like the divergence of S equal F in L2, but even the stronger condition, namely the divergence can be replaced by the gradient on sufficiently regular domains. But yet it is still an open question how to use this regularity on S in numerical discretizations. But I will point this out later again. The second difficulty is exactly the roughness of the right-hand side. So what can we expect on the regularity of the solution? If you just check carefully in the paper of Vera and Heitwen, they proved that a Wiener process exactly belongs to the Bezoff scale, where you have 1/2 time derivative measured almost on, like, it is almost bounded, but it is not quite. So phi 2 here, phi 2 of t is e to t squared minus 1, meaning that it has exponential moments, squared exponential moments, but it is not, so you need to measure it on this refined Nikolsky scale infinity. So if you are below this threshold, that's like the second result. If you want to lower the infinity scale here to some r, you immediately lose that you have 1/2 derivative. So if you put here a minus, you can get the result. But if you want to have here 1/2 exactly, you should work on the Nikolsky scale here. And because on the right-hand side, we have a general operator G of U dW, so which we just shortly abbreviate with IW acting on G of U, we need to understand, okay, what does the stochastic integral operator preserve if we put like a bounded function in it? Meaning that, so if you put a bounded function in time in it, then roughly speaking, the output of the stochastic integral is as regular as the Brownian motion. So you have, again, 1/2 derivative measured in the exponential Nikolsky scale. And just to give a decoupling result if you have a semilinear equation, and so like G, which is just smooth in space, and dW on the right hand side, so you can nicely decouple the influence of the operator G on the space scale and on the time scale. Then you can get smoothness of solution in space with values, so like C 1/2 minus and C infinity in time and in space. This has been done by Hoffmann-Nova in this paper. Why is it difficult? So why is it difficult to like generalize concepts from deterministic theory to the stochastic setting? And this is essentially due to the lack of chain rule. So if you, so in the simplest case, just take a solution to this parabolic equation. So you have time derivative is equal to this differential operator. The key step to find nice regularity results is to find a good functional f that like has nice commutator properties. So if this guy, for example, has a sign, then you immediately know that if f of u in 0 has regularity, then also at later times f of u will have the regularity. So in some sense, at least the regularity of f is preserved. And just to give an example, so if the differential operator is Laplacian, we maybe choose f of u equal to like the L2 inner product, then we exactly see that this contribution is minus the gradient squared. So in particular, this is satisfied, and we see that the L2 norm is at least bounded by the initial L2 norm. But you can come up with different ones. So maybe you take here some LP norm to the power P, or even some gradient norms, gradient U to the power Q. And then most of the times it boils down to understanding the interaction of the derivative of this functional f acting on the spatial operator of U itself. And in the stochastic case, you have like more conditions you need to fulfill in order to preserve the regularity, because not only do you see the same operator that is seen here from deterministic theory, but you get a second order operator that is due to Ito correction. So not only do you need to have nice commutator properties of the derivative of f with respect to the differential operator of u, but you also need to have nice properties of the second derivative of f, sorry, here's an f missing, acting on like the evaluation of g of u. And in this way, one needs to couple like the conditions on G you need to enforce on the stochastic forcing and the second order contribution in order to still say that, for example, this df of u has a sign, because then you get the same statement as in the deterministic case. And here on the stochastic side, one needs to be careful, because if one tries to get like an infinity estimates, then usually this third contribution is also there that needs to be coped with. So it's now like a fight of three terms that need to be dealt with in order to get the result, rather than in the deterministic theory only of one contribution. Okay, what has been done? So just to give some of the results for the P Laplace equation, classical monotone operator theory, for example, in the paper of Liu and Wöckner, they expanded like the L2 energy, and they get canonically that the solution is bounded in L2 and belongs to LPW1P. The L2 framework is usually not enough to get like the regularity results for in order to get time regularity results. We need strong solutions, meaning that the divergence of, so this equation can be interpreted pointwise in X rather than just tested against smooth test functions. And this has been done by Guess in his paper, and he expanded the P energy. And here we need to restrict to P bigger or equal to 2. Because stochastic integration in spaces below, so in LP spaces below 2, is difficult, meaning that you need to find the right substitution for the E2 isometry in order to supplement, in order to identify the limits on what should be the proper limit of the stochastic integral. Yeah, a second contribution was by Bright, and he expanded like the L2 energy, and on the L2 scale, because you have the nice the nice square root operator, you always see the V operator appearing. And he got the L infinity bound in L2 W1P, and you get one derivative of V measured in L2. And what basically what I did is, if you have the strong energy, the strong formulation of the solution, meaning that if you know that this one is in L2, you can get time regularity of the solution, because you just can put this to the right and now see, okay, the evolution of U is basically the evolution of this operator, the divergence of S and the stochastic integral operator. So as long as you have a nice bound on the divergence of S and the integral operator, you kind of almost immediately get this result. In order to get this result, you need to work a little bit more. But the key point is that like 1/2 derivative in time is proportional to exactly the divergence of this guy in space. And we will see this later on. So what is now the canonical energy to look at if we want to study the P Laplace, the P Stokes system? So first of all, we take a function which is now divergence free, and we define the P energy measured with respect to the symmetric gradient. And a simple computation shows that the first Gaussian derivative is just given by this one. And because this guy is a symmetric operator, S of U, you can just replace here the symmetric gradient with the classical gradient. And if we partially integrate, we are back to the formulation that the divergence as EU psi shall be psi. So you see naturally the P Laplace or the P Stokes operator appearing here. And yeah, similarly, the quadratic variation is given by not the quadratic variation, the second order contribution, so which is here d2j of U acting on U minus V squared, is proportional to exactly this kind of energy. So saying that a solution to this non-perturbed equation is exactly equivalent to the gradient flow of the energy induced by the operator J. So it has a close connection to the P Laplace system. And in particular, the results of Benjamin Guess, who developed like regularity theory for gradient flow equations, is applicable. So what can we now expect for the P Stokes system? Because it is so close to the P Laplace system. And just to give some results, so the existence of weak solutions in the additive case, so this G of U is just a G, dW, has been done in this paper by Yoshida and co-author. And later, he generalized this to the gradient scale, also in the additive loss case. Yeah, and then further generalization was, okay, if we now do not allow for only additive noise, where the solution is, so the noise coefficient is independent of solutions, but we go for G's that depends on U. This has been done by Bright. Yeah, just on the L2 scale. So he constructed martingale solutions for the full P Navier-Stokes equation, so even with convection. And this has then been generalized to electrogeological fluids. So the P in essentially this norm also depends on the position and the time. So it's like a further generalization. So in some sense, they get that the V of EU itself belongs to W12. So you have one derivative of this nonlinear square root operator of the function, symmetric gradient. But what can we expect for the time derivative? So this is an L2 in time. And the key, as already mentioned, is to consider this energy. And because we expand like so exactly this energy, G of U, which is EU P to the power P. Because we work on this LP scale, we also need to assume a growth condition of G with respect to the LP scale. And exactly this condition here tells us that we cannot take like gradient noise, because if in simplest case, if G of U is just U, you see that you have here the W1P norm hitting the W1P norm here. So if this one is linear, you are exactly in this framework, but if G of U would be like a gradient, so if G of U would be some gradient of U, if you take a gradient here, you would take a squared gradient here, and you can no longer get this bound on the, like without the second derivative of U appearing. So one would need to relax this condition, and this is, not easy. In particular, one needs to be careful with all this constant appearing in order to be able to cope with exactly these terms that depend on the second derivatives of U. But if you have this sublinear growth assumption in this energy space and some Lipschitz condition, and this Lipschitz condition usually gives you that like the stochastic integral operator is well defined and solution is going to be unique, then you can check that solutions satisfy this a priori estimate, meaning that you have here an L infinity W1P estimate time at x, and you get that the projection of the divergence of SAU is in L2. And what you need is finite energy at initial time. So you need that U0 is not only in L2, but it should also be in W1P 0 diff. So what does it help if the divergence of the projection is in L2? The projection of the divergence, basically we just take the projection from the left to the right and now say, okay, if we want to find regularity of U, we need to find bounds on the regularity of the first component and on the second component. And what we use is essentially the mapping properties of the stochastic integral, because this guy is IW of the projection of G of U. So if we know that PG of U is bounded as is an L2 L infinity, we can use the results from Verard and Andriat, where they bound exactly this integral operator, so the stochastic integral operator. Then we see that U itself will belong to this space. So meaning it has 1/2 derivative measured on this exponential Minkowski scale. And how do we obtain regularity for the nonlinear square root operator? There we heavily use the equivalence condition here, which is again S of A minus S of B, tested against A minus B, is equivalent to the increment in in B. So in particular, if you put gradients, so A and B are gradients, you get the increment in this is proportional to this one. So here we have only one partial integrate per parts. If we now use the strong formulation of the equation here, so this is strong formulation, you get once a term that hits itself, so it has already a nice sign. Roughly speaking, this one can be neglected. And you get something which requires to have the understanding of the stochastic integral in LP. So because this S operator usually belongs to LP prime, you need a nice regularity theory of the stochastic integral in LP. And therefore, we need to restrict ourselves to the case PE bigger or equal than 2, because otherwise stochastic integration is just more involved. Yeah. And what can we say about the pressure? Because pressure is later reconstructed as soon as we have constructed the velocity field. We basically decompose the pressure into two components. The first one only sees the nonlinear tensor S, and the second one sees like whatever is the gradient contribution of the nonlinear of the noise. And we already see that it is not expected of pi to be a function, because pi is formally looking like white noise. So it is like on the distributional scale. And what can we do if we now understand how G acts as a function on the solution? We just, again, need to understand the mapping properties of the stochastic integral operator in order to see that the stochastic integral, the stochastic pressure, will have -1/2 derivatives, also measured on this Minkowski scale. But what we gain is that it is the stochastic component is highly irregular in time, but it is more regular in space compared to the deterministic one, because the deterministic one only belongs to LP, while the stochastic one has a classical gradient. So there it's quite delicate to understand, can we cope this with this irregularity in time with somehow the improved regularity in space in order to still get nice algorithms that exploit this. That's basically the last part of this talk. Here I want to give you an example how regularity in this nonlinear context can be used to give a bound on the convergence rates for one possible discretization. So because this V, so the operator V, V of EU, only is B1/2 in time with values in this Minkowski space L2, we cannot say that in general the map T mapping to this quantity is continuous. And in particular, most of the times, the troublemaker is the action of this nonlinear operator S and the test function psi. Because this map is not continuous, we first regularize the equation. So we just take a grid of uniform grid, and if you have a solution, U at T0, U at T1, we can also just take U at T minus U at T minus tau and just average this along some interval. And this, guys, we then just call U at mean U at n minus mean at U n minus 1. If we do this and just forget that this has been derived formally by the analytic solution, we can propose the following algorithm. So meaning that the incremental evolution of the approximation sees like a tau psi step evaluated of the, sorry, here should be in symmetric gradient. So it's an implicit discretization of the nonlinear operator S. And then we discretize our right-hand side, which in general is multiplicative. And we evaluate it at 2 former times because we use as an increment the averaged Wiener processes. So meaning that delta 1W, NW is like W at n minus W at n minus 1, which sees function values of W on the interval Tn minus 2 Tn. So because it sees 2 points, so 2 intervals, we need to wait 2 intervals in order to accurately construct an adapted coefficient to the filtration that sees this guy. And then basically this theorem is the theorem that tells you if you have regular solutions. So the assumption is if you know your solution is regular, that you have 1/2 derivative in time of both the function u and the square root operator v. And if you have 1 derivative in space, so you see 1 derivative in space, 1 derivative in space, then you effectively can say that the approximation you construct via the algorithm measured on the L infinity L2 scale and on the gradient scale decays of rate 1, or like 1/2 in time, and of order 1 in space. So you have a one-to-one correspondence between how many derivatives do you have in time and space, and what is the rate of the convergence of the simplest algorithms. And we need to assume this technical condition that the L2 projection has this property, and so you have like a nonlinear stability result of the L2 projection, which can be verified for conforming discretizations, but for not this in general is a non-trivial condition that one needs to check in. So as soon as you fix like the discretization, you need to check whether this condition is satisfied or not. And the key point behind like exactly divergence-free approximations is that the low regular pressure is not seen. So this equivalence, this lower bound, this estimate, it depends on the regularity we assume here on the top, but it does not depend on the pressure regularity. So kind of like exactly divergence-free approximations are desirable if you want to exactly split also the approximation, so the approximate equation into a nice velocity equation and a nice pressure equation. Yeah. And just to like summarize, in the in this nonlinear context, you have in general two scales of the equation. So you have like du minus divergence as gradient u. So this one is homogeneous of degree p minus 2, p minus 2, and this is homogeneous of degree 1. So one needs to be careful with, one needs to be careful with what is natural and what is, so meaning if you test this first guy with the Laplacian, you get the square root operator here. And from this guy, you get like the L2 norm. If you test this first guy with the P Laplacian, divergence of S, you get the expansion of the P energy here. And you get from this guy already a nice contribution because it is of square type. And what, just to highlight this again, so this is the energy that is natural for the grade for U. This is the natural regularity for the grade for this nonlinear operator V if you test with the Laplacian. And if you test with the P Laplacian itself, this is the natural regularity in time for U. So you see it's bounded with values in W1P, but it is almost C1 half Hölder regular with values in L2. And you get also some time regularity of V, which is exactly this B1 half. And just to be complete, these are the estimates on the weak framework for the pressure. So you have like minus one half derivative of the stochastic contribution, but you gain one derivative in space. And this guy is like regular in time because it's in LP prime, but not that much regular in space because it's in LP prime also in space. And what one now can do is try to generalize things to the case P below 2. And as already mentioned, P below 2 require substantial new techniques to treat the stochastic integral because there the classical concept is just not defined. A second thing that one might want to study is how is pressure, so how does the regularity transfer to the pressure in the context of strong solutions? So because these regularity results are on the level of weak solutions. Maybe related to this pressure question is the regularity of the gradient of the nonlinear operator S. So having a control on the L2 norm of this guy in general does not give you any information on the full divergence of EU, nor does it give you any information on the even stronger SEU. So if you want to have like results for this or this, you need to come up with new ideas. And if you can achieve something through this, another question is, can you use it in the approximation. So can you come up with a scheme that uses regularity in S in order to measure like the error in different norms or improve the convergence speeds or yeah. So it's many things are not clear yet in this direction. And yeah, here are some like main references. So this is my thesis where you can basically get an you get a comprehensive summary on why should you care about stochastic equations and on the regularity results for the P-Laplace and the P-Stoch system. Here you can find some results on exactly the last part of this talk where we discussed like approximation procedures. And these two are the regularity results. Maybe this one here is the main reference of today's talk where you want to, if you want to have a look at what time regularities is expected for the symmetric stochastic P-Stoch system. And in particular, what time regularity can be used then for the estimate of numerical algorithms. And that's basically it. I'm happy to answer any questions if you have some.
So thank you very much for a very interesting talk. And are there any questions?
Please raise your hand if you have questions.
So perhaps I will start. I have one question. At the beginning, you showed us the version of stochastic Navier-Stokes equation by Rozowski and Mikulevičius, or Mikulevičius and Rozowski. And they derived this equation. They claim that it covers, say, stochastic Navier-Stokes equation that must be of this form that they obtain. And then they have Stratonovich integral. Then you consider your problem with the Ito integral, and then there is an argument that because of the Ito correction, the second derivative appears, and this is the source of major difficulties. Now, with Stratonovich integral, you wouldn't have this, there would be cancellation, and the second order derivative would disappear. So wouldn't it be easier to do it that way?
I guess so. The main reason why they study,
of course, they study a simpler equation in a way because they have linear stress, but yeah.
Yeah, the key point is if you test this equation with U itself, you can use the antisymmetry of this operator again, and it will drop out, meaning that you have pathwise the same energy estimates as for the deterministic equation, which is really, really favorable.
Mm-hmm.
But it's not clear how these things evolve like with higher derivatives, meaning that if you would take a gradient of here, you take a gradient here, can you test with the gradient here? I mean,
yeah.
You lose already here the stuff.
Yeah, I see. Mm-hmm. Thanks.
But people are really considering this thing also in its Stratonovich formulation because you have exactly the pathwise energy estimates, which lead to improved things.
Mm-hmm.
I have also some questions. May I, Ben?
Yeah, sure, of course. Please ask.
So firstly, this B space, B½ is a Bezoff space, is it right, in time?
Yes, exactly.
Okay. And then the second question I do have is, can it be that the turbulence case, so the convection term, or the nonlinearity in Navier-Stokes, for the P-Laplacian must be different, basically, that it should be associated to the nonlinearity of S, basically?
No, I don't think so, because I think in the physical motivation, it's really sitting like, we have it. So this guy should be considered together as a material derivative of like the underlying flow. But this guy, so you could write this as, I don't know, dt of u equal to some divergence of S, where this is in general just viscous stress. term.
Mhm.
But yeah, it's really like this one shall be put together, because yeah, this is just the correction you need to take if you want to consider Eulerian coordinates into Lagrangian coordinates.
Mhm.
And the structure of the stress gives you like how the internal forces of the system act. So I'm at least naively answering, I don't think that this needs to be different.
Okay, good. Thanks.
Are
But
there any?
maybe,
Yeah, sorry.
yeah, maybe I add something. So maybe this transport type needs to be changed in the general context for the P Laplace, because yeah, no, it's not. Yeah, the structure of this and this are heavily linked to. Yeah, I don't want to comment on this.
Mhm.
Mhm.
Are there any other questions? I have one more minor question. You have on one slide, you show a corollary. Maybe you can go forward.
This,
Yes, it's here. What do you mean by dv here? This is in the integral formula. This is an Ito differential, or d should be in front of the integral?
yes, this is basically, you have an increment in this guy. So it's like v of EU at t plus h minus BEU at t squared. And then you have a dt integral in t.
Okay.
I.
Uh-huh.
So, and this is a function in h, and kind of like
Yeah.
this as well, and this is yeah.
Mm-hmm.
Then it's about checking how is the decay in h of the right-hand sides compared to the left-hand side.
Are there any other questions? If not, I would like to thank the speaker and all participants again, and we can meet at the coffee break in a few minutes. Everyone should have received the link to the coffee break in the information email. So thank you. If there are no any other question, I will close the meeting.